All right, so in this video, we're going to look at calculating the relative extrema in specifically two variables, although these same processes will work with more. We're going to look a little bit at the three variable case very briefly. It is a little bit more complicated when you go beyond the 2 dimensions. You need a little bit more linear algebra, but there is a way to do it. And so we'll look at that at least conceptually, but we'll walk through an example of the 2 variable case. All right, so let's look at our first example. We want to first find the critical points and then determine eventually whether they are relative maxima, relative minima, or in the higher order case, we also have to consider that they might be saddle points. Now, if we take our first set of partial derivatives, the derivative with respect to x is going to be 2x minus y plus 3, and then all of these terms go to 0. The partial derivative of y with respect of f with respect to y is going to be negative x. This one's 0, that one's 0, minus 6, and then plus 8y. Now, to get the critical points, we set both of these equal to 0, and we need both of them to be 0 at the same time. So we're solving a system of equations. And so I've rearranged my system. I put the constants on the other side of the equation, and then I have multiplied my second equation by 2 so that the negative 2x and the 2x can cancel, and I end up with y equals 3/5. And then if I plug y back into one of my equations to solve for x, then I end up with x is negative 6/5. Now that's our critical point. Now to determine, there's only one in this case because this is a second order problem, second degree equation, and so there can be only one critical point. If you have like a third degree term, if you have 1 third degree term, that will double the number of critical points. If you have 2 third degree terms, that will double it again. And so you could have as many as 4 critical points. There could be less, but the maximum number of critical points goes up. Each time you increase the degree, you increase the number of available critical points in that dimension. And therefore, if you had x to the 4th, you would have 3 potentially in the x direction. And then if you had, let's say, y squared, then you would have potentially 1 in that direction. So there'd be potentially 3 total. But if you have 3 in each direction, you could have as many as 9. So in this case, we have only the 1. Now, to find out whether this is a minimum, a maximum, or a saddle point, we're going to need the second derivatives. And the second derivatives are going to be the same if they're mixed partials. So we only have to find one of them. The second derivative with respect to x, if we go back to our fx equation, the second derivative, the derivative of this one with respect to x is just 2. And that's what we have here. The derivative of x with respect to y is going to be negative 1. And the same thing, if we took the derivative for y with respect to x, we would also get negative 1. And then we need the derivative for y with respect to y again. So that second derivative will give us an 8. So those are our second partials. And then sometimes this is referred to as the D test. Sometimes it's called the second partials test. But basically, and what we're really doing from a linear algebra perspective is we're putting all of these values in a matrix with the derivatives for x on top and the derivatives for y on the bottom, and we're finding the determinant of that matrix. But what it comes out to is fxx times fyy minus fxy squared. And whatever that value is going to tell us something about whether this is a max or a min on the one hand, or a critical point or a saddle point on the other. Now, if the D is positive, then it's either a max or a min. And if D is negative, then it's a saddle point. If D is 0, then we have to use other means. This would typically involve things like gradient fields, level curves, things like that, because that's the equivalent of the first derivative test in multivariable calculus. In textbooks, they typically may not ask you to go beyond that if the test fails. You just say it's not, you can't determine it. But really, if you needed to determine it, you would go to the gradient field and you would determine it that way. Now here we're going to plug in our values. Our second derivative for x was 2. Our second derivative for y was 8. That gives us 16. And then we're going to subtract the -1 quantity squared, and we get 15. This is positive. So the critical point is either a max or a min. In this scenario, both of our partial derivatives for x, twice, the second derivative for x and second derivative for y, they will both have to be the same sign. And they're either going to be both positive or both negative. And so often the textbooks will just say, we'll look at one of them. If it's positive, if it's greater than 0, the graph is going to be concave up, and therefore the critical point is a minimum. If they are both concave, if they're both negative, then the graph is concave down, like an upside down parabola, and therefore you get a maximum. If they're going in opposite directions, one is positive, one is negative, which can't happen if the D value is positive, then that would be a saddle point. But those are not the only cases, because of course this mixed partial term can have an impact on that saddle point characteristic. So but these being opposite signs guarantees that it is a saddle point. But if they're the same sign, but this mixed partial term is much larger, you can still get a saddle point. And if we actually look at the graph in 3 dimensions, we see that indeed the graph does in fact have a minimum. Now we can look at a second example where we have more higher order terms. So there will be more than one critical point. And these ones, sometimes just keeping track of all the algebra can be a little bit tricky. So it can be helpful to sort of make tables of things in order to keep track of stuff. So the procedure, though, doesn't really change. We take our partial derivative with respect to x. That one's 0. Then this one is going to give us a -6yx or xy. This one is going to give us -6x. This one will give us 0. This one will give us -6x, and this will give us 0 again. The derivative with respect to y, this will be our 3y squared. This one will be -3x squared, because the y goes away. This will be -6, and this will be 0 and 0. Now, again, we have to solve it like a system of equations. So for this first scenario, you set each thing equal to 0, and I divided out the -6 in this first problem. And then the thing that you have to keep in mind is that you can't just divide things unless they're constants. If one of the variables is 0, you can't divide by 0. So you would need to factor. So this first equation, I factored, and I came up with 2 possible scenarios. Either x is 0 or y is -1. In the second equation, I've taken out a 3, but I can't really go any further at that point. But what I can do now is I can take these 2 possible values that I got from my first equation, I can plug those into the second equation and see what gets paired with x equals 0. If I plug in x equals 0, where is that second equation going to be equal to 0 itself? Or if I plug in y equals -1, is that going to give me a different value for x, where those 2 could be paired together? So that's what we do here. I started out plugging in x equals 0, and then I end up with y squared minus 2y. I can factor that, and so I get two possible combinations. If x is 0, y can be 0, that's 0, 0. Or if x is 0, y can be negative 2. So that's two possible critical points from that condition. And then the alternative is I can plug in y equals negative 1 into that second equation. And if I simplify that, I'm going to end up with x squared is equal to 3, or x is plus and minus the square root of 3. So both of those have y coordinates of negative 1, but now I have squared plus and minus square root of 3 as possible scenarios. Now, again, I got 4 points here because I actually have cubics. I have a cubic here and I have a cubic term here. And so I ended up with 4 potential critical points that I need to verify. So I'm going to go back and I'm going to take my second partials in order to determine what each of these critical points is doing. Now, in the previous example, we had only one critical point and our d-test was just a constant. And so it only, we didn't have to apply it to individual points. Here, our d-test is going to depend on variable values. And so it's going to give us different values for each of the potential critical points. So I need to take my second derivative for x. So if I go back up here, take the derivative for x again, I'm going to get negative 6y minus 6, which I got here. If I need to take the derivative for x for this expression, or for y for this expression, I'm just going to get negative 6x. This one is going to be 0. And then if I take the second, go to the second derivative, the one for y, and take the derivative for y again, then I'm going to get, going back up here, there's a 6y here, and I'm also going to get a 6 from here. This one will be 0. So these are my 3 second partials, one variable, and then the mixed partial. Now, remember that our formula for the d-test is fxx times fxy minus fxy squared. So fxx, fyy minus fxy squared. Now, what I would recommend is that you find the values for each of the critical points and then calculate your d. You can, of course, come up with a general formula, but then in this case, we would have some multiplying and things going along. And so that would be the foiling and the algebra would be a little messier than just working with constants. So here what I've done is I've taken my 0, 0 critical point and I've evaluated my second derivative for x at 0, 0, and I got negative 6. My partial derivative, mixed partial at 0, 0, and I got 0. And my second partial for y at 0, 0, and ended up with negative 6. And so the d-test for that will be negative 6 times negative 6 minus 0 is 36. For the 0, negative 2 scenario, again, I plugged those 2 points up here. I'm going to get 12 minus 6, which is positive 6. This is going to give me 0 again. And plugging in negative 0, negative 2 here, I'm going to end up with, since this is positive 6, this will be negative 12. And I end up with negative 18. So 6 times negative 18 minus 0, that's going to be a negative. And then I do the same thing down here. My positive square root of 3 and negative 1. I only have a y here, so I plug that in. I end up with a 0. And here, I'm going to plug in the same thing here. I'm going to get this crazy square root of 3, but that's fine. And then here, I'm going to plug this in, and I'm going to get negative 12. But 0 times negative 12 is 0, and so I'm going to subtract my mixed partial, and I'm going to get a negative number. And then for this one, same deal. Plug this in, I get a 0. I plug this into my mixed partial, I get the square root. I'm going to plug this one in to my second derivative for y, and I'm going to get negative 12, but it's 0 times negative 12 minus the square of the mixed partial, and I'm going to get a negative. So again, we're going to look at our values. For the 0, 0, we got a positive, so that is either a max or a min. For the 0, negative 2, I ended up with a negative 108, so this is a saddle point. For the other two that both give the same d value, that's this guy squared with the negative, so I'm subtracting it. They both give me negative 8, so they are also saddle points. So I end up with 3 saddle points and 1 max or min. If I look at these values, they are both negative, so my 0, 0 is actually a maximum. And if I actually look at the graph, I can see the maximum on there, and then my other saddle points as the things run off to infinity in various directions. Now, in order to do 3 variables, you have to bring in a little bit of linear algebra. So if you're, again, this is typically not covered in a multivariable calculus course, but I was curious about it, so I investigated. The d-test formula can be written essentially as the determinant. You put your derivatives, your second derivatives that you take for x and you take for y. Your mixed partials are on the opposite diagonal, and the one variable cases where you did the same variable twice are in the regular diagonal. And then you take the determinant, which is these two minus these two. And so you end up with this formula. In the 3 variable case, you would essentially do the same thing, but you would have 3 derivatives. And then you would essentially find this expression, this D standing for determinant in this case. You would find these basically the same way you find a triple scalar product. And you get this really crazy expression. And you would, again, you would have the same scenario where if this was depending on your sign of the determinant and things like that, you would get some conclusions. Now, many more things can happen in a 3 variable case, and of course, this is impossible to visualize. But you could have 2 directions that were increasing and one that was decreasing, and you're going to need much more linear algebra. They could be all increasing. You're going to need much more linear algebra in order to actually determine the characteristics of what these critical points are doing. You would actually need to find the eigenvalues and things like that. Again, we're not going to worry about that, but I just thought it was curious. It was interesting. Like, there is a way to do this with 3 variables. We just don't do it typically in calculus because it needs we can't just sort of circumvent the linear algebra and say, here's a formula. Things get much more complicated, and we actually need the linear algebra to make sense of this.